Okay, so when we're dealing with complex numbers can, ironically, be very difficult to get your head around. Right? They are, by their very nature, complex. Okay, and because we're dealing with this thing, it kind of brings about this imaginary part. It is very difficult to picture. So one of the things we use to help us is this thing called an Argand diagram. Okay, and what we can do is we can plot our complex number z, where it's equal to x plus iy, and we've seen it before in the form z equals a plus ib. So all we've done is we've just kind of changed out those variables. We've swapped a and b for x and y. Okay, doesn't really matter at this stage, but we're going to use that to help us. So what we can do is we are going to draw out a set of axes. Okay, and as always, I've got x and y in it. I'm going to take a point on this plane, draw out to it from the origin. That's my origin, and there's my point. What I can do now is, for completion's sake, we can work out where that is. If I just drop a wee perpendicular down, we can see that its height, some value of y, its length along here, some value of x, and its angle, just going to give theta. Okay, now what we can do, thinking about our vector stuff, is we can find the length of O to P, which we'll refer to as R, and we also call it the modulus of z, which we can denote z stuck in between two little bars. Okay, now there are a whole load of different names for it because it can serve a whole load of different purposes. So we can refer to it as r, we can refer to it as the modulus of z, we can write it as z with the two bars. So we'll be expected to remember all of them. We can find it by doing a little bit of Pythagoras, because I've just made a little right angle triangle there. So r is equal to the square root of x squared plus y squared. Okay, how does that relate to my complex number? Well, remember, it was made up of x plus iy. So when we're dealing with our complex plane, my x-axis is my real axis, y-axis deals with the imaginary part. Okay, and I'm going to end up writing over my same things there, so we're going to stop at imag. Alright, when we're doing it, it is very important that you somehow define which one is which. Okay, you need to tell us that you're dealing with your x-axis as the real things, your y-axis is the imaginary things. Okay, so that's very important as we're moving forward. Other things we can work out, well, we can work out the size of the rotation on the x-axis. It's called the argument of z, essentially the angle. We can work out the angle, is what we're saying there. So my angle theta is equal to the inverse tan of y over x, and hopefully that's not anything too shocking because that should just follow your SOHCAHTOA stuff from National 4. When we're dealing with this, your angle is going to fall between minus pi, that's strictly bigger than minus pi, that's less than or equal to pi. Okay, and remembering, for those of us that still don't like radians, we are dealing from minus 180 degrees up to 180 degrees. We can also, by using a little bit of simple trig, we can work out some values for these. Okay, and if we are following the mechanics course, or if we've been doing physics, or even just remember it from last year, we should find this a little bit straightforward. So we can actually find the value for x is equal to r cos theta, and that y is equal to r sine theta. Again, we've just used a bit of SOHCAHTOA here to get us to work these out. Okay, so remember, your sine is the opposite over hypotenuse, so sine of the angle is the opposite, which is y over that. Rearranged it, and we found equations for them. As a result, this z equals x plus iy can be written in a different form, so it can also be written as z equals r lots of cos theta plus I sine theta. So all I've done is I've substituted x equals r cos theta and y equals r sine theta into that equation there. I've taken r out as a common factor, and it's left me with what's there. Okay, moving on, we can find that the size of the argument, as we will have spotted from when we did wave functions, when we were solving our trig equations before, it can be multiples of 360, or it can be multiples of 2 pi, okay, as we are going around. So what we do is we refer to the value of the argument of z, arg z there, which lies between minus pi and pi, as our principal argument. So whenever we're asked to draw these, you'll be expected to refer to the principal argument. Okay, and what we're doing is we're looking for that one that falls in the range minus 180 up to 180. Okay, so if your answer comes out to be something like 270, 280 degrees, things that you've normally been fine with dealing with, you need to remember and change it. Okay, so that's going to be one of the things that is going to trip you up here. So let us consider an example. So we want to find the modulus of, and let's come up with a complex number. We've got z equals 3 plus 4i. First thing I'm going to do, and it's not essential for the question, but I'm just going to give it a quick sketch. Okay, remembering I've got my imaginary part, I've got my real part. So I've got 3 along real, 4 at my imaginary bit. Okay, so if I was to make my little right angle triangle again, it would be 3, 4. So how do I find that? R is equal to the square root of x squared plus y squared. So remember z was equal to x plus yi. We'll match it up here. And so r is equal to the square root of 3 squared plus 4 squared, which is 5. Okay, hopefully we spotted that. It was a 3, 4, 5 triangle earlier, but if the worst came to it, you worked it out and you'd have gotten there eventually. What we also need to find, or we're going to find, is we're going to find the argument. So we're going to find arg z, that's how we're going to shorten this, and that, my angle, was equal to the inverse tan of y over x. So we've got the inverse tan of my y value, which was 4, over my x value, which was 3, so inverse tan 4/3, and that is going to give me 53.1 degrees, which is the same as 0.95 radians. No, it's not. Typed that in my calculator wrong. 0.93. There you go. Happens to the best of us kids. 0.93 radians. So what we do is we found it and we've kept it as the big A. It's the argument. We don't know what value it's going to give us yet. It might give us a value that we don't like. Okay, but my 53.1 degrees, my 0.93 radians, is in our principal range. It is between minus pi and pi. It is between minus 180 and 180. So we can say then that it is the arg of z, literally, that's equal to 0.93 radians. Okay, second one then, we are going to find the argument of z equals minus 3 minus 4i. Okay, and what we've done is we've got the same numbery bits, we've just changed the symbols. So again, I'm going to draw just a quickly sketch so that I can get my head around what's happening. And so I've got minus 3 minus 4, and so it's actually going to go that way this time. Okay, I've got minus 3 minus 4. So the modulus is going to be the same as above. Okay, we'll write that down just for the sake of the notes. Okay, because the modulus just tells us the length of this complex number. So the length of it hasn't changed. We've changed the direction, we've changed the way that it points. But crucially, it is still the same length. So r was equal to the square root of x squared plus y squared, which is the square root of this time minus 3 squared plus minus 4 squared, which is still 5. Here I want to find the argument of z, and we're always starting with a capital A, right? If it works out to be nice, we can change it to a lowercase letter, but we're starting with a capital A just in case. So the argument of z was equal to the inverse tan y over x. So theta is equal to the inverse tan minus 4 over minus 3. And that is going to give me 0.93 radians. Okay, essentially it's giving me the exact same thing as it was before. Okay, why is that? Well, it's finding for me that angle. Okay, but that is not what we want. We need to find that angle. And so I need to do 0.93 plus pi. Okay, again, such is the beauty of teaching you in the cast diagram or whatever it's called. The letters still fit on each of these quadrants, and so that one down there should be tan. My minus 4, my minus 3, the minuses cancel out. Give me this positive number, and that's why we're getting the same value here. Okay, anyway, once I've added this together, I am going to end up getting 4.069. And that is now bigger than my range of minus pi up to pi. Okay, and hopefully that is very apparent because I've added on pi. So whatever this was takes it beyond that limit. So in order to find my principal argument, arg z, we are going to need to do 4.069 minus 2 pi. And that is going to give me minus 2.21. Okay, and that's just my answer there to 3 significant factors. So just like we used to do it with our trig things, and we would have to make sure that we were doing it within the right range, we'd find the values, we'd have to add on another 360 or take away 360 depending on where we were. That's the same thing that's going on here. Okay, that's what it is that we're looking at doing, and we should remember that when we are dealing with it, we're kind of starting with it there. So there is still my 0 degrees, and my minus pi point is over there. So the fact that it's pointing down there shows me that it should be very close to the minus pi. Start at minus pi, I go round to 0, keep going through my positive things to pi. So that's the bit that's telling me it should be very close to this minus pi, and that's the angle, what we've found. Okay, third one. We want to express z equals 2 plus 2i in the form r lots cos theta plus I sine theta. There you go, you almost even forgot that we'd written that. So two things we need. We need r, we need theta. And so actually it is exactly the same as these other ones where we ask you to find the modulus and the argument, because those are the two parts that we need. So I want to find r. I can do the square root of 2 squared plus 2 squared, which is the square root of 8, which hopefully we know is 2 root 2. I'm going to find my angle, so that is the inverse tan of 2 over 2, 2 over 2 being 1, and so where is tan 1? Well, it happens at 45 degrees, pi over 4. If you're that way inclined, and so that means z, my complex number, is 2 root 2, that's the cos of 45 plus I sine 45. Or if you wanted to, z equals 2 root 2, that's the cos pi over 4 plus I sine pi over 4. Okay, and those are the two most important things that you can find from your complex number. You can find its modulus, and you can find its argument. And if you're ever not sure what you should be doing, draw yourself a wee picture to try and help remind you.